Morning, year 11 or afternoon, depending on when you're watching this. I hope you're well. I hope you are looking forward to September studying here at Ashton Sixth. And I just wanted to go through a little taster of what's to come here in September, looking at something that you're familiar with, something that you've studied at GCSE, but bridging a gap between that and A-level. So taking something we've looked at and just extending the idea a little further. So we're going to look at the shapes of molecules today. So up on the screen, you'll see a molecule that you're familiar with, that you've studied at GCSE. So this is methane. It is the carbon bonded to 4 hydrogens. Okay, so this was the way that we could display it. Another version of it is you looked at dot and cross diagrams, so actually showing those covalent bonds, that shared pair of electrons, and each carbon has a shared pair of electrons to a hydrogen. So we've got 4 covalent bonds. But I've said, what's the problem? Okay, so what is the issue with representing those molecules in them 2 different ways? Okay, your teacher even might have talked about limitations at GCSE. So have a think for a moment. What might my issue and how can we extend that at A-level? So today I want to look at giving you this idea of spatial awareness. Okay, so we live in a 3-dimensional world. Okay, so these are 2-dimensional images projecting or trying to show you 3-dimensional shapes. Okay, so the issue is they are flat. Okay, it gives you no indication of the shape of the molecule. And also, if you look here, it gives you a slight incorrect bit of information. Okay, so those of you that have like done maths, here you can see that the bond angle, the angle between the carbons and the hydrogens, appears to be 90 degrees. Okay, and simply it's not the case. Okay, so there is an issue with this model. It works at GCSE, but we just need to bridge and show you the spatial awareness, okay, that you might have. So right now this is a little bit better. Okay, so again, this is still my molecule of methane, and let's go over to my visualizer. Here it is. Okay, so this is my molecule of methane. And from this point of view here, and the one that I've just shared on the screen, okay, this is how we're trying to represent it, flat, okay? And here, you can almost see that if you look there, the bond angle, if I show in this representation, is 90 degrees, okay? But as you can see, that clearly isn't the case. Okay, so if we look at this molecule, you can see it is 3-dimensional. It actually has this tetrahedral shape. Okay, so around the carbon. Okay, and in fact, it's a symmetrical molecule. So let's look at taking that a step further today. So because this is a bridging exercise, I want you to recap what you've done at GCSE. I want you to pause this. I want you to spend 5 minutes. I want you to have a go at drawing dot and cross diagrams, because they are a fantastic tool to help you think about and visualizing the shapes of the molecule. Okay, notice at the end there, I've put one in red. That is a challenge one, and you will see why in a minute. So pause me, only spend like 5 minutes on this. We're going to go through them. So let's have a look. So first of all, let's focus on carbon. We've already looked at that. Okay, so we've got this idea, and I've shown you in reality what it looks like. Okay, But again, so let's look at BF3. Okay, we've got this two-dimensional image of a three-dimensional shape. In actual fact, that is a flat molecule, but within a three-dimensional space, and we'll look at that in a moment. Another molecule that you've looked at is water. Okay, so here you've got your hydrogen bonded to two oxygen, okay, your two bonding pairs, but here, remember, we have these electrons in pairs here not involved in bonding, okay, we call them lone pairs, okay. So if I now show you what that looks like, okay, you might have seen this at GCSE. So that is a bent molecule, or V-shaped molecules here. So you might have even used this at GCSE. However, I'm going to show you this one here. So you can see here that you've got your two hydrogens here. But now I want to show you that those two lone pairs, okay, that are not involved with bonding, are actually influencing a three-dimensional shape. So although it looks very similar to our tetrahedron, okay, in actual fact, if we just look there, that is where we get that bent molecule from, okay. So what are the lone pairs doing? They are repelling. There is a repulsive effect here, okay. So they're forcing the electrons closer to each other. That's incredibly important. That is influencing the shape. You know that the electrons are negatively charged, okay, and they don't want to, when you put two negatives next to each other, they repel, okay, and they are repelling equally or as far as possible. In actual fact, these are having a greater effect, which is causing them to push towards each other, and so you get a bond angle of 104.5. Let's look at another shape, okay? Another molecule that you've looked at GCSE, ammonia, okay? So this time, just as before, we've got three bonding, three shared pairs of electrons, three covalent bonds. So it should look a little bit like this one. But what you can see is we have, just like in water, we have this shared, this pair of electrons not involved in bonding. So if I show you that now, what does that look like? Well, we've got a molecule here. So from above, how we draw it on the board, it looks flat, okay? We look at it in space, though, we can see we've got a trigonal pyramidal. Okay, so it's almost flat, but it's bent towards the center. They are repelling. There is a lone pair on the top here, and they're forcing the electrons towards each other. They have a greater repulsive effect. And finally, did you attempt my challenge? Okay, this is a very complex molecule. So sulfur hexafluoride, okay? This is my dot and cross diagram. What do you notice? Okay, this is mind-blowing. Okay, the rules might have been oversimplified at GCSE. If you notice here, we've got 2, 4, 6, 8, 10, 12. We've got 12 electrons in our outer shell. So what we're going to look at A level is expanding the octet. Okay, so we weren't wrong at GCSE, we just oversimplified what we were looking at, okay? So here, what does that look like in reality? So here we have this fantastic shape, okay? So we have an octahedral, okay? So you can see it is a symmetrical molecule. We have an equal bond angle as before of 90 degrees between each of them. And you might be saying, well, why is it called an octahedral? Okay, it's got 6, but it's the actual, we're thinking about the shapes of the molecules, and it actually has 8 sides. Okay, this is an octahedral, so it's got 8 faces. Okay, so let's look at so a linear molecule. Okay, for example, CO2. Okay, why is this 180 degrees, a bond angle? Because the electrons, because we've got 2, they are negatively charged. They want to be as far away as possible from each other, so they are repelling. Okay, they are repelling 180 degrees. Okay, so you've got a 3-dimensional space. We've looked at your tetrahedral, so this is kind of showing you I'm bridging the gap between it, the flat 2-dimensional shape, and what actually the molecule looks like. Okay, your trigonal planar. Okay, very similar, because it is a flat molecule. However, the bond angles, okay, this time, because these are all repelling equally from each other, there's 120 degrees. Our water molecule, our unusual, our special, we know water is a fantastic, unusual molecule, absolutely fundamental for life. And when you do biology as well, you will see that. This unusual V-shaped or bent molecule. Trigonal bipyramidal, okay, so it's not trigonal planar. Okay, we've got this fantastic molecule here. So if it's got 5, trigonal bipyramidal, double pyramid. So we've got 2 bond angles here, 120 along the axial plane and 180 on the equatorial. And our unbelievable, really good example of an octahedral. So we've done water, so let's go through an example for you. So let's say you were given, your teacher gave you PCl3 as an example. How would we go about looking at the shape or determining the 3-dimensional shape, giving you that spatial awareness? So PCl3. So let's look how we would do that. So here we'd use our periodic table. So phosphorus. Notice I'm still going to use the dot and cross diagram because it is a useful tool. So here I've got phosphorus in group 5. So it has 5 electrons on the outer shell. Okay, chlorine in group 7, so there are 7 on the outer shell. Okay, so we know that this is covalently bonded, so I'm going to do a shared pair of electrons. 2, 4, 5, 6, 7. 1 chlorine. Okay, so let's repeat it twice more. 2, 4, 5, 6, 7. 2, 4, 6. Okay, so I've used my dot and cross diagram. However, we need to think, so how many? 1, 2, 3 bonding pairs. So earlier I told you 3 bonding pairs, that would be trigonal planar. So there, trigonal planar, okay, with a bond angle of 120. But wait, we haven't discussed, we have a lone pair now, this pair of electrons not doing anything, okay, and they have a really influential pushing, okay, so you've got your electrons all trying to spread out equally around the phosphorus, but then you've got this lone pair here. They have a greater influence. Okay, so in actual fact, what we get is a molecule that looks like this. Okay, a slightly bent molecule. Okay, so we've got a bond angle that looks like 120 from our drawing, but is in actual fact 107. Okay, so 107, we can accurately determine that. So we've got a trigonal pyramidal shape. Okay, so let's look at one more example. So the molecule on the screen, you've probably not seen before, but let's try and apply what we've looked at, this 3D nature of shapes, and improve our spatial awareness. So we've got astatine fluoride. So what do we know? Well, we know we can do a dot cross diagram to help us look at that. So astatine fluoride, so let's go through, oops, and use my whiteboard. So astatine has, let's just move 5 electrons on its outer shell. Okay, and we know we've got 5 fluorines, so we are going to go 1, 2, 3, 4, 5. So they are the covalent bonds to the fluorines. We know fluorine is in group 7, so it's got 7 electrons. I've already put one there, so we can use that to add onto each one 6 more to complete the outer shell. Okay, so already we can use this model to give us an idea, a scaffold to what this is going to look like. Okay, so now 1, 2, 3, 4, we have 5 bonding pairs. But again, this gives us no indication of the actual 3D nature of the shape. But this molecule, we've got lots of electron density. The electrons want to repel each other, and they're going to do that equally around the astatine. Okay, so earlier we discussed this. We get a molecule where the only way they can all be around the molecule equally is this shape here. Okay, so this 3D. A 2D, 3D shape onto a 2D. I'm just going to add this here. Okay, so they're all repelling each other equally. So in terms of our shape, we've got a trigonal triangle here, bipyramidal. Okay, so actually 2 triangles. So you've got one at the top, one at the bottom. And in terms of the bond angles, earlier we said 90 degrees between the fluorines, but there is also 120. So we've got 2 bond angles. So hopefully that gives you a flavour of what's to come. There's a few more exercises. So going back, name these shapes as practice and explain the difference in the bond angle. So think about what we've talked about, them lone pairs, what influence are they having on the angle and repulsion. And you can summarize all this, it's entirely optional, into this table. So this is how it would look. So you can go back through the slides that will be shared with this as well. So that's all I wanted to do. So just to let you know that that is a bridging exercise, so taking something that you're familiar with at GCSE and then just looking at how we can expand it and improve it for our A-level thinking. Thanks very much, and I will hopefully see you in September. Thanks, bye.